Inscribed quadrilateral, and what's true about an inscribed quadrilateral?
The opposite angles are supplementary.
Yep. Basically, that generates two equations. So 7x plus 1 plus 2y plus 74 equals 180. And 2y plus 100 plus 6x minus 10 equals 180. And so we have two variables, but we have two equations, so we're going to be able to solve. If we only had one, we couldn't. Remember, you have to have the same number of true equations or relationships as the number of variables you wish to solve for. But we need to clean these up a little. So first is going to be 7x plus 2y. And then we'll add the 1 and the 74 to get 75, and then subtract it from 180. So we have 105 on that side. And then 2y plus, and here's where we want to write it in the same order. So 6x plus 2y, and then subtract 10 from 100, we get 90, and then subtract that over. Okay. So those two bottom equations are in standard form, we call it. Okay? This is, for this one, the best way to do this. You could do substitution where you isolate either x or y and plug it into the other equation, but that would be pretty messy in this case since both, like if I think about getting this x by itself, I would have to divide everything by 7. So I would have a negative 2/7 and a 105/7. That might be a whole number, but, and then down here, I would have like 2/6, 96. Anyway, it's going to be uglier than doing it this way. Actually, with this, it's pretty slick. Here's why. We have these two y coordinate or y terms with the same coefficient. So if we use elimination, we can get rid of the y's and only have x's. And this is where we add or subtract vertically. So how do we get rid of those two y's? Good. And I always tell students to make that real big so that you know that you're subtracting all the way across. So 7x minus 6x is just x. Of course, the y is 0. And then we get 105 minus 90. So x is 15. How do we get y? Yeah, we plug x back in. Where would you like to do that? Like currently we have 4 equations that would work.
Small one.
Yeah, but like which one?
7x.
Okay. So we're going to plug 15 in for the x. Oops. And now we just have an equation with just y. So we'll just solve. And this is kind of weird, but 105 is 7 times 15. And so we subtract and we'll get 0, and so y is just 0. Okay. How'd you do? We'll be doing systems in Algebra 2 when we come back from Christmas break, I mean. This class will get to systems probably that second week back. This kind of stuff, but also systems of, we call them 3 variable systems, so not just x and y, but also z. And so we have 3 equations, and we have to like combine and combine and combine and combine and combine. And it's cool. It's a lot more work than this, but it's built off of this. So nothing in it is not really any harder. It's just more of it. But it's pretty cool to be able to solve for 3 variables. How'd you do? Anybody get x is 15, y is 0? Yeah, good, good, good. Okay. I think at this point in geometry, we're pretty close to the end. You can see how even though it's geometry, there's a lot of algebra in it too. You've seen that throughout the year. Like here we're solving systems, we've solved quadratics, we've solved just regular linear equations. Geometry is kind of there to set up the relationship, and then algebra is our solving tool. So yesterday we talked about inscribed angles. So I just want to review those real quick. Remember that angle has a vertex on the circle. Its measure is half of the intercepted arc. And that kind of held true throughout. Any two inscribed angles that intercept the same arc are congruent. Inscribed angle of a diameter is a diameter intercepts a 180-degree arc, so the inscribed angle is always 90. And then the tangent chord relationship was the same. It's still, the angle is still half of the intercepted arc. It just looks a little different the way the interception is done. And then we just worked with this last one on our starter. Okay, so that said, let's look at your homework problems. Now, this was not everybody brought it, but hopefully if you at least have done it, you'll remember your answers. I'm just pulling it up here. I forgot to do that. The first section was just a vocab review. So all of those words we've dealt with at this point. So go ahead and check them. We haven't defined a secant, but line AB is a secant. I told you that, but we haven't written it formally in our notes yet. Vocabulary is a pretty important part of this unit, probably more so than some of the other ones we've done, just because there's so much new vocabulary. Any questions on any of those? Okay. And then in terms of the bottom, this is a relatively simple picture. Like I say relatively to other ones, but I tried to show where stuff came from. So measure of arc AB is 180 minus 36. How do we know it's 180? Like what's the 180 coming from? This is an arc, right? Yeah, because we have a CA is a diameter. How do I know that? Yeah, in this case it shows you the center. Sometimes it doesn't, and it'll say, assume it's a diameter, that kind of thing. Anyway, keep an eye out for those diameters. They really help. Okay. Number 12, measure of arc CD. This time I used 360. Where did that come from? The whole way around the entire circle arc, right? Okay. All right, I'll let you check the rest. If you have a question about what my notation means, let me know. I'll say this. VAT stands for what?
Vertical angles.
Yeah, that's the vertical angles. It looks like for 7, that's what we're going to talk about today. 7 and 8. So if you didn't get those, that's fine. You just copy them down. you gonna go back and do them? Yeah. Any questions? Okay. Give me 2 angle names that we've talked about. Isla, give me one. Good. So inscribed angle. Zeke, tell me what the relationship it is with something we could know. Like, what do we know about inscribed angles?
Angle with the on the circle.
Good. Braden, how about the size of it?
The size of the
Inscribed. Okay, good. Mackenzie, tell us what else about the size of an inscribed angle. Like the main idea. No? That's only a specific case. What is always true about an inscribed angle? Not just the diameter inscribed angle, but all. Lyra. Sorry, Tim. Actually, Tim, we'll go with you. No, the size of it. Like, how do we know it? You're right. That's true. It's half of the intercepted arc. Okay? Lock that in. Inscribed angles are a big one. What is another type of angle we've talked about? Central angle. Lyra, what's true about central angles? Yeah, true. Like, I'm kind of going with like, how do we solve with them? So, what's true about a central angle is measure. Yeah, it's the same as the arc. So inscribed is half, central is same. Okay, keep studying those notes. What do we know about side lengths or any lengths in a circle? What have we studied that has to do with length? Zeke. Arc length. Tell us the formula. Try not to look.
Theta divided by 360 times pi r squared.
Oh, close. Pi.
Diameter.
Yeah, good. So the theta fraction of the circumference, right? Okay. Kenzie, what else have we talked about length? Or something besides angles? No, that was an angle actually. It was degrees. Arc measure was degrees.
The diameter of the radius?
Yeah, diameter and radius. Can you pick something from this year? Keep looking. We'll come back. Do you remember? Good job studying your notes. Tobin, how about you? Give me a length-based something that we've learned about circles.
Circumference.
Okay, but I want something from sophomore geometry, not 7th grade geometry.
The area of a segment?
Yeah, okay. Tell us about area of a segment. We're coming back to you, Tobin.
Area is the ice cream to the cone.
Okay. I like how you think. The ice cream in the cone. How do we solve for it generally?
Find the segment and the no, it's the 8 triangle minus 8 sector equal
Sector minus triangle. Yep. Good. Isla, what else have we talked about that has to do with length?
chords.
Yeah. Tell us about that. Which of the chord relationships did we use to solve for lengths of chords, or maybe a radius or a distance from center?
What do you mean, which of the chords?
Well, I think we had 4 chord relationships. Which one was the one that had to do with length? Well, the one that we solved for mainly.
chords and radius and diameter?
Yeah, that one, which is perpendicular. Yeah, good job. Tobin, what else?
Tangent.
Yeah, some tangent stuff in there, right? What kind of, how did we solve for lengths with tangents?
Tangent and radius.
Yeah, which is what? What's true about that?
It's perpendicular.
Perpendicular, so tangent, radius kind of set situations. We had right triangles, so we were doing probably Pythagorean theorem. Okay, remember that was, let me go back to this real quick. Okay, tangent and radius, just reminding you that sometimes you had like x and then 5 and you had, I don't know, maybe something like that, and you had to add the x plus 5 and square it in the Pythagorean theorem. So we ended up with stuff like this, right? And you had to distribute. You couldn't just square each term, but you had to distribute. Okay, and then we solved. So that was tangent stuff. The one Isla told us about with the chord was this kind. Okay, and it ended up with similar kinds of maybe not doubling, but squaring a binomial. Like maybe this was x plus 3 or something, right? And r was 5, and maybe this was 2. Okay? Similar kind of geometry, or similar kind of algebra, rather. Okay. So lots of lengths, lots of angles. We have 2 more things to talk about. One of them is angles, one of them is lengths. And again, it's so critical to identify which you're talking about or which the problem is about before you start solving, because the properties can really lead you the wrong way if not. So let's do the angles first. I don't think we'll probably not get to the side length today. My plan is to talk about the secant angles today, secant lengths tomorrow, and then review part of tomorrow, review Thursday, test Friday. The only problem with that is that Friday is not probably long enough to do our test, so we'll see. There might be. Not probably for certain people. All right, first of all, we need to define what a secant is. And this definition is, we're using it with circles, but it goes beyond that. We use this in other math too. So a secant line is a line that intersects a curve. I'm going to write circle for this unit, but understand that this is also for a curve, okay? Twice. So things like if I just draw a line through the circle, how is this different than a chord then? Remember, it has end points on the circle. So so like she said, it stays within. Okay, we could have secants coming from the same point, like that. And we're going to find a relationship between those, but that's what secants are. The reason we wrote curve, in Algebra 2, maybe we'll have a function that looks like this. And we're going to talk about something called average rate of change. We abbreviate AROC, A-R-O-C. Okay, and so maybe we want to know the average rate of change between these 2 points. So that line, the red line, is called a secant line. And it goes through the curve. I guess technically in this case it would go through 3 times, but we're talking about the 2 points where it touches. Okay. So just on this picture right here, this thing is not working today. There we go. Do you see an angle right here? Okay, so that angle is related to this arc and this arc. So it intersects the circle twice. So it's creating 2 little mini arcs. Do you see that? And so there's a relationship between those 2 arc lengths and the angle. We could also, I don't want to busy that picture. Maybe we have 2 secants that intersect somewhere inside the circle. Well, now we have that angle, which we know is vertical to this angle. Those are congruent. But those are related to those 2 arcs. So with secants, you're always looking at 2 arcs instead of just 1. Okay? And there's a relationship that's kind of, well, it's a consistent relationship is what I want to say. So first one, we'll say secant. So actually, before we do that, let's make sure we're clear that this is the angles side of secants. Because then we'll come back and do all these with lengths as well. Am I in your way? Okay. So the first one is if they intersect inside. That was the one I just. So just draw 2. It doesn't. Your picture doesn't have to be just like mine, but just draw 2 secant lines that intersect somewhere inside of the circle. And then let's give these points some names. A, B, C, D, E. Okay. Here's our relationship for these kind. Actually, before we do that, let's highlight 2 arcs. I'm going to go with those. We could also do the left and right angles as well. But we're going to use this one, measure of angle ACB. Okay, here's the familiar part, or at least somewhat, is half, just like an inscribed angle. Seriously, this thing is jumpy. Okay, it's half of the 2 highlighted arcs. So half of arc AB plus arc, the measure of arc DE. And this, obviously the letters will change, but this concept is a formula, so maybe box it so it stands out. In other words, it's half of the 2 arcs that those angles are intersecting. Okay, so keep in mind that there are vertical angles there. Angle DCE is congruent to angle ACB. And why is that? Yeah. So it's the same. And I'm writing that because what if I asked you for angle DCE instead? Well, it's the same exact calculation because it's vertical to the angle ACB. Okay, again, we could go the other way with this. I'm not going to mess up this picture, like make it more busy. But if we wanted these 2 sideways angles, it would just be the measure of those 2 arcs that it intersects. Okay? Does that make sense? So it's just half of their sum. Okay, if they intersect outside, the good news is it's another half relationship. This time we're going to draw 3 different versions. Formula. So the first one is secant. So something like this. Do you see 2 intercepted arcs? That one and that one. For each of these, here's the terminology I want you to use. We're going to call this from the angle. This is the farther angle or farther arc, and this is the near arc for theta. Do you see what I mean by near and far? Like one's closer to the angle. Okay, next one. We're going to have a secant tangent pair. Again, we're creating a near and a far arc. Can you guys tell me what else we could do? We did secant, tangent. What's the third one? We did that one. Well, no, we didn't. Secant chord is not the one we're doing. Let's see. Secant chord, like that would be kind of like the first one, right? It would be this version. Or like obviously they have to intersect to make angles. Good thought, but that would be the same as that first version. So this one's going to be secant, or excuse me, tangent. Something like that. Let me write the name. I forgot to do that. Okay. If you look at just the left side of the picture, it looks the same. So here's what I mean. Like if we took this off just for a second, all of those angles are 2 lines coming together outside of the circle. That's what we mean by exterior, or being formed outside of the circle. It looks the same. It's just this pointy angle somewhere out there. So it doesn't totally matter which version it is. You need to be on the lookout when you're solving for an angle formed outside of the circle. That's all. Because the equation or the formula for this is the same in all cases. And it's going to be measure of angle theta. We'll call it. That letter can change. Again, it's 1/2 the measure of the far arc minus the near arc. So that again is a formula. Probably should box that. So the measure of the angle is half of the difference this time whereas before it was the sum. So it's pretty darn close, but that's a big difference. So I'm going to make sure that's clear. So subtract versus add in the other one. Otherwise, it's kind of similar. Any questions on those? We're adding a lot. Isn't this a lot of stuff about circles? It's crazy. We have a few more things. I think we'll save it for tomorrow. We'll start off easy. It says measure of arc AD is 155. We know that's degrees. And BC is 61. What is the measure of angle 1? So which version is this? Yep, secant angles in or out? Inside. Okay? So we'll do this real quick and then we'll have our break. So measure of angle 1, is it the sum or the difference? Yep, so we just add these two and take half of it. Okay? Go ahead and take your break. I'll fill this out while you're doing that.
This year,
Yeah.
we got this done.
Okay. Prove. Do you want to prove?
No.
You guys always say no. That was adamant out of you. I'm gonna put that one on the test. Just for you.
Next 3 weeks.
All right. What are these two lines called on this left page? Left problem. What are the two lines? Huh? Secant tangent. Yep. Does it matter? No. So this is an exterior angle. So what's the equation? Measure of angle B equals what? Yep, which is DA minus CA, measure of arc CA. Well, no, we're not given CA. How do we find it? Well, we don't have one. Okay. So measure of arc CA equals 360 minus 151 minus 139. What is that, 290, I think? Together, I mean? 290, yeah. So that's 70. What's 151 minus 70? 81. What's half of 81? And this is degrees because it's an angle. All right, what are those two lines called in the second one? Those are both secants. What's the formula, the equation? Actually, I'm going to have you solve this one. I'll pause there and won't say anything. Okay, so I did a little bit of the work. This is an exterior angle for my secants. So it's the measure of the far minus the measure of the near times a half. Remember to write both sides of your formula always. So this time we fill in that the measure of angle J is 34. And then we have our far and our near, this time in x form. Be careful when you subtract. So I put brackets around the 3x minus 5 because we have to subtract both of them, not just the 3x. Okay, once you do that, you get inside, you get 6x minus 3x, so that's 3x, and then 6 minus negative 5, that's 11. Okay, now how do we solve from there? Goal to get that x out of parentheses. How do we do that? Yeah. What? It what? I mean, you can. You'd get 3 halves x plus 11 halves. Probably most people don't want to do it that way. You can though. It's not a wrong step. So you guys get in the habit of looking for ways to make math better, not just done. Which means, how do we get rid of the half without distributing it? Yeah, if we multiply by 2, those cancel out, which is faster. Now we have to do it to the other side so that we are balanced. Okay, 68 on that side. And now we don't have to deal with fractions at all. Okay, from here we'll subtract 11. And we'll get 57. And then divide by 3. And we'll get 19 for x. Now that's not what the problem wanted us to find. If you look, it says find the measure of arc LM. So we take our 19 back in here. So 6 times 19 plus 6. 120, I think. How'd you do? Raise your hand if you got x is 19. Okay. Anybody willing to share where you went wrong?
I accidentally added and subtracted.
Oh, back here?
Yeah.
Okay. Yeah, that's that. It's so confusing because it's different.
I subtracted 6 minus 5, not 6 minus negative 5.
Okay. Think the brackets would help? Yeah, so on this, if you're ever solving for x inside with that minus, use brackets. Anybody else? Okay. So that's how this fairly easy concept can be made a little bit harder. And of course, what if we put, what if our 3x and our 6x were squared, and now we have a quadratic to solve. So we could do it that way, perhaps. Okay, lots of variety there. All right, is this one interior or exterior? Interior, okay. And it wants us to solve for this arc. So what would our formula, our equation rather, look like? Who wants to set it up for us? Okay, go ahead.
Would it just be 107 equals 1/2? 74? Or would it be 74?
Well, they're added, so it doesn't matter. Sure.
But I don't know the other.
Well, that's what we're solving for.
Yeah.
Like that, right? Or you could call it, don't call it, probably wouldn't call it x since there's an x in the points around the circle. But we could call it something else, like A for arc or something, right? But since this is interior and they're being added, we don't have to worry about which order we do. Anyway, how would you get that A out of parentheses? Still, yeah, if we want to get rid of that 1/2, we'll multiply by 2, right? And do it on the other side. And now it's just subtraction. I think that's 140. I think. Okay, real quick to point this out. Let's say the problem just says, what is the measure of arc A or arc WX? If you read this as a central angle, do you see how that would be wrong? But it's close, right? Like the point for the vertex is pretty close to the center. So be careful on that. That would be a warning on this. But you got to make sure you're looking at secant angles and not, or in fact, this is chord angles, but it's the same idea. But not central. All right. Is this, we'll just quickly on this one, is this plus or minus? This is minus, right? Because this is exterior. Okay. So interior is plus. I don't know if I have any other good ones. Yeah. All right, so in terms of practice on this, what time are we done? We still have a while, 30 minutes. Why don't you pull out your Chromebooks while I post, and I didn't print this, and that I didn't print it on purpose. I want you to practice a few of these on the sheet on here, and then maybe for like 20 minutes or so, and then I want to hand you the next Circle of Doom practice, okay? What? Smile. Smile. So it's going to be the one that says circles, secant, tangent, angles, hard. It says hard. It's actually not any different than what we've been doing. I'm not sure why it says that. And you're going to start on number 7. So this is page 2. And I'm going to tell you, I don't want you to do all of them. So start on 7, and then I'll tell you which ones to do from there. So let me go post this so you can get it. Of course, I'll come back and update it later on. All right, so click on the worksheet 10.5. Start on page 2, number 7. And then do, I'll actually put it up here, so. On the post, I'll put it on the post.